right?
Yes.
I can't really.
Not a problem.
You know, right, well, let's. All right, all here. Scroll.
And by the way, I should have.
Ah.
There you go. So you got palm and
You gotta push the button underneath that too.
Yeah.
That one.
What did you go do?
Now you can put the laser. Well, we're going.
Yeah, hey, turn it, go do it. Okay. Okay, let's get started. Whenever we get snow here in Illinois, the only solution is to bring somebody from sunny Arizona over to cure things. Who better today than Professor Rogier Windhorst? Rogier got his PhD at the University of Leiden in the Netherlands. Spent many years working at Las Campanas and other observing facilities, but he's mostly known for his work, of course, with NASA and HST and JWST and probably other NASA space telescopes. He's been one of the interdisciplinary NASA scientists. And interdisciplinary here really is the key word. He's worked on galaxy evolution, on cosmology, and many other fields. If you do an ADS search, you'll notice that he's published with several faculty in this department. Many of whom were not faculty when he published with them, so he's also been around this game a very long time. That's recognized by the fact that he's one of the Regents professors at Arizona State, one of the more senior people that is there, and is apparently one of the directors of the Center for Cosmology. So, Roger, please take this on.
Thank you, everybody, for inviting me. It's great to be here. My first time this part of Illinois. So we're going to talk about the world of Webb, cosmic circle of life, and seeing through the eyes of Einstein. This is on behalf of a very large number of folks that I've worked with in the last number of years when the data started flowing, but even before that time, when JWST was still in the design and testing stage to define the science program, students, postdocs, research scientists, and another 10 more over 18 time zones. Liam will join me tomorrow in the Pearls Zoom, where we talk about our papers. So I'll say that I'll keep it as simple as possible. Gave this talk to the physics department at ASU a month ago in slightly simplified form, and they thought it was fine. So there will be a dog and pony part, and then a more specific part. The cosmic circle of life is more dog and pony. The rest will be a little more specific. I'll try to avoid math, but for those of you who do not think in these regular terms, I'll have one equation here. That whenever I talk about distances, the field of view that you see here is typically the distance which would be the size distance I talk about divided by 1,000. So I talk about these galaxies being an average of 10 billion light years away. Field of view would be roughly 10 million light years across that distance. Yeah, so we'll keep it simple just for the sake of sanity. So we'll talk about Webb in orbit as of almost 4 years ago. Then the cosmic circle of life and viewing the universe through the eyes of Einstein. And that's about as far as I'll get. And I'll have a few spare charts, one of which is noticeable if we have time, on a unique complementarity of Hubble and Webb in their roles. The talk is listed there in a link, and I will forward that link to Gotham if I haven't already. So the general warning is that asking NASA for Hubble images is like taking a sip from a fire hydrant. Yes, and asking NASA for Webb images is like taking a sip from the Niagara Falls. I didn't have a good picture of somebody trying that, but children, please don't do this at home. We will be overwhelmed with images, don't blame me. Telescope is working and it produces terabytes a day, and there it goes. I'll spare you the 20 years before launch. We have a separate talk on that, lessons learned from JWST. We'll just go with the successful launch on Christmas Day, 5 in the morning, Arizona time, from Kourou, French Guiana. The Europeans, ESA was a significant part of, it still is, of Webb, as well as the Canadian Space Agency. This is Webb 8 minutes into launch. I suppose I need to click OK for something. Over the Gulf of Aden, Saudi Arabia, Africa, just minutes before it deployed its solar array, not the sun shield that came days later. This is the last picture taken from the upper stage of the Ariane 5 launch vehicle, the camera they had on board there. I had proposed to do more. There's a few more seats here. You take some of these seats. Yeah, so I had proposed to have more onboard cameras to see if the one went well, but there was no astronaut servicing this thing. It didn't actually work at the Earth. It went straight to L2, which was a 2-month journey. So it was a significant launch and a very successful once they used precisely 0 sigma of excess fuel launching this thing. And as a consequence, we didn't need to use very much propellant to get to L2. And the consequence of that is that we have now 27 years worth of propellant on board. So as long as all the other hardware holds up, we're not going to run out of gas anytime soon. In February, this was the first selfie taken by the telescope. So there's 18 hexagonal mirrors, all made out of beryllium, 1.35 meter across, each 6.5 meter edge to edge, with of course an imprint of the support boom of the secondary is hanging above the primary. I will spare you all the details of how this was made. Once you're in orbit and you take a picture of a star, first time you do that, you see 18 out of focus images. This particular mirror, this one over here, was more out of focus than that one and that one. So the first thing to do was to take the actuators, the hexapods underneath each of the 1.35 meter beryllium mirrors and push and pull at 7 degrees of freedom, rotate, translate, and radius of curvature to get each one of these properly aligned to within tens of nanometers precision. Once you do that, these images become sharp, but you still have 18 of them. And of course, you don't want 18 stars, you want 1 star. So then you tilt each mirror until all 18 images are co-aligned. And there is your point spread function, which is indeed the Fourier transform of this hexagonal mirror with its several millimeter spacing. And then, of course, these support bars produce an extra diffraction spike. Oops, I'm going the wrong direction. So you actually have 8 diffraction spikes, 6 ones of which are the most prominent, but there's a horizontal one, which is the Fourier transform of one of the support arms for the secondary mirror. So there we are. Now we have a focused telescope. This was about March of 22, 3.5 years ago. So one of the focus stars here, my buddies in Goddard Space Flight said they were very excited about this. They were all exoplanet astronomers and engineers. They didn't actually care about the star while they did. They had to focus. They cared more about all the red galaxies behind the stars, of which there were very many. Yeah, so Webb is looking back in time. They got very excited about this. And we'll get more about that later. So then we had a family portrait of everything, not quite done at the same time because you can't operate instruments at the same time, but not all of them. The prime workhorse, the near infrared camera made by Masha Ricci, who's spoken here before from U of A. The Canadian fine guiding sensor, where these panels hold the telescope still for rotation and translation during long exposures, with a backup Grism spectrograph called NIRS, also made by the Canadians, and then the European near-infrared spectrometer, which can also image, as well as the mid-infrared instrument that works from 5 to 29 microns. All the others work between 0.9 and 5 microns. So you see a range of wavelengths here. Each one was used just for fun in different wavelengths. And this was looking at the Large Magellanic Cloud in the South Ecliptic Pole. That was April 22. Good progress made compared to the 85 centimeter Spitzer Space Telescope. The same field in the LMC, much better resolution. And you can't really see this bridge of dust and gas between these stars, but you can see very nicely over here. So cosmic star formation in action, a very dense star field. So before we get to the cosmic circle of life, I can't resist to show you this chart of the periodic system that you learned in high school. We need to get this part straight. This is not a real periodic table that is there in nature. You might have learned about this in college, but just for the record, hydrogen, helium in blue, a little bit of lithium formed in the Big Bang, low mass dying stars like the sun will produce the green elements, exploding massive star supernova will produce the brown or orange elements, merging neutron stars, and we have learned from LIGO, produce the purple elements, cosmic ray fission gives rise to boron, and human synthesis makes everything beyond plutonium, plus a few others like that. So hydrogen, helium, the only chemical elements made in the Big Bang, except for lithium, all heavier elements made by dying stars. 4 categories that I mentioned. So the real periodic system is this one. Yeah, in the right proportions. Hydrogen, helium, and the rest. Physicists will call this chemical elements. Chemists may have the same word. I call it dust, or stardust, or metals, depending on what side of astrophysics you're on. But this is the real cosmic periodic system. And remember that all of these were formed inside either massive stars or low mass stars like the sun at the end of their lifetime. So we're going to give you some examples of that, and then we'll get to the eyes of Einstein. First, let's put this all in cosmic perspective. Here's what looks like the Maddow diagram as a function of redshift between 0 and 14, which is kind of the highest JWST as seen in the cosmic age. Big Bang is over there, today is over here. You can see that both the growth of cosmic stars, this blue curve, as well as the growth of active galactic nuclei, the green curve, as well as the supernova rates for type 1 in red, type 2 to N in orange, peaks around redshift 2, which is 10 billion years back in the past, when the universe was only 3 or 3.5 billion years old. So for the standard HST filter set, which typically runs between 0.2 and 1 microns with a little bit of infrared here, also doable, but much better done with JWST. Those are the prime filters to look at optically unobscured star formation, like these star forming galaxies, all good measure, put at redshift 1.9, the median redshift in average deep field. And then, of course, the dustier galaxies or the older galaxies at the same redshift, shown over here in red, are best seen with the NIRCam bluer red filters, and of course, at the longer wavelengths, especially for the dusty objects, also with MIRI. I should say that because the sky background gets a lot brighter here past 4 microns, that it's harder to observe, but it is a unique wavelength range. So HST best samples the unobscured star formation history and black hole growth for the last 10 billion years, while JW best samples the obscured parts, especially in the first 3 giga years. So a bit of a technical chart, but it is an important one. If you had 0 resolution with your eyes, but you could observe all the wavelengths between gamma rays and radio, you would see something like this. The sky would contain zodiacal light, which is this green spectrum, and then the Planck curve, dust emission at 280 degrees or so in the solar system, and of course the microwave background not shown here. And well below that level, by factors of hundreds or so, would be the integrated light of galaxies, which is these red dots, and the integrated light of dust in galaxies and in active galactic nuclei, where quasars, elliptical galaxies, spirals each contribute to that part. And then there has been some diffuse light observed by various techniques that claim that there is maybe some additional diffuse light in the universe, not related to stars, galaxies, or AGN. The important point here is that the energy in cosmic star formation and in AGN, the integral of the red curve, is 48% of the total energy budget, and the energy in dust is 52%. In other words, that 1% of the baryons in the previous correct periodic system produced more than half the photon energy in the universe. That's important to realize. So dust matters, yeah, even though it's a tiny part of the periodic system. So now let's get to the cosmic circle of life. This is the good old Eagle Nebula. You've all seen it. It was made by my good friend and colleague Jeff Hester and Professor Paul Scowen at ASU. This was with Whitefield camera 2 in the optical, pillars of dust, light years long, sculpted by a cluster of hot stars in the Eagle Nebula of the field not shown here. So this is between 0.3 and 0.9 microns. This is the near infrared image between 1 and 5 microns. It's the same pillars. You can obviously see through the dust much more clearly, like sunsets are red. Dust transmits the red light more clearly than the blue light. And you can indeed see that at the end of all these fingers here, new stars are being formed, being sculpted by the star cluster that is up north outside the field of view. So this is the cradle of cosmic star formation. And this image made it onto a US postage stamp. I'm going to keep some record of time here. Gotham, you want me if I run over or if there's some questions? Yeah, okay, see that, good. I will be happy to take questions halfway through because that's when we go to the eyes of Einstein. So that was the first one of the more dramatic images. This is the same tilted with merely the mid-infrared. Now there's far fewer stars behind this cloud because stars don't shine very well in the mid-infrared, as you saw in that fly's eye image before. But you can see the copious amount of dust here, and indeed at the end of some of these dust fingers, new stars are forming. These are stars like the sun that are forming courtesy of the more massive stars that are in this case outside the field of view. Here you see this more clearly now in the LMC, 160,000 light years away, 30 around this star cluster that has excavated this giant region here in this beautiful cloud. Young massive stars also trigger the formation of other stars in their neighborhood. So this is going to be an Eagle Nebula in another galaxy. There is the star cluster with Whitefield camera 3, blue young hot stars. Here at the end of this finger, you can't really see it in the optical here, is a star like the sun. There it is in the infrared, right there, forming at the end of the finger. So cosmic star formation happens the same way in all environments, in different galaxies. Okay, so this is probably one of the most stunning images that we saw initially from the near-infrared camera, cosmic cliffs of star formation. Again, the same principle. Now you can see the hot stars that are sculpting this shock front of previous gas and dust deposited during the formation of this galaxy. And indeed, inside these regions, better visible even still in the mid-infrared, new stars are forming. So I think I call this cosmic circle of life for reasons we'll see in a minute. Think of this as a beachhead, and the blue, of course, is not an ocean, but it's the ultraviolet light, and the brown is not the sand, but the dust out of which new stars and planets are forming. Here in the mid-infrared, you see that better. A couple of new stars already lighting up. Most stars form in binaries or multiple systems. The sun is a bit rare in the sense that it's not a binary. This is also seen in the trapezium of Orion Nebula, cosmic cliff-like structure here. And then inside this box is a small region where a nodule formed new stars that contain the carbon chain methylation. My chemistry is a little rusty, so I couldn't write that down. But we see the elements of building blocks of organic material here, not life, just building blocks. The Hourglass Nebula is a protoplanetary nebula. That would be a star that is forming here in this center of the debris disk, and while it's forming, it is illuminating the surrounding gas, which has an hourglass shape. This is a low mass star, about 30% of the sun's mass, only 100,000 years old. and it has a surrounding disk of accreting gas, circumstellar disk. Eventually it will start shining like an M star, a little cooler than the sun. Here's the row of UV dark cloud figures, both with NIRCam and MIRI. Closest stellar nursery at 456 light years. New stars are forming, and in the center of this the big Haro object is a young star that is also in the process of forming its debris disk. This particular system contains PAHs, polycyclic aromatic hydrocarbons, that you can see with the spectrographs. And it is chemically a messy system. This one is two Herbig-Haros 4647 with jet expelled materials. The central star is forming there. Star formation is a messy process. There's inflow and outflow of gas and dust. Remember that. There's a cosmic circle of life. And of course, once the star is formed, this one you can see with the unaided eye, not in this much glory, but this is the star Fomalhaut, southern hemisphere in the winter, has a debris disk. The star itself is suppressed with the coronagraph. That's like a cold finger that is held in the appropriate place of the focal plane where the starlight itself is gone. It's a hole, and you can see the surrounding disk. This is a real image. In that disk, at the Saturn-like distance, is a little nodule forming, better seen at the shorter compared to the longer wavelength. And that is a protoplanet, like Jupiter and Saturn would have formed around the sun. Here's another system like that at AU-MIG, 32 light years edge on. The whole thing is about 60 AU across. And again, the central star, which was right here, is suppressed at the coronagraph. And you can see the debris disk very clearly edge on. It's somewhat larger, but not a whole lot larger than the solar system. It's also a lot more messy. You know, most of this stuff hasn't become planets yet, but it will. So here's some direct images of planets. Again, star with this telephone number. The coronagraph suppresses the starlight. You see the surrounding planet. It has some side lobes. Those are artifacts from the coronagraph. But there's clearly a planet there. It's about 10 Jupiter masses, 15 megayears in age. And this is an image between 3 and 15 microns. Taking spectra of these things will not be, but teams. This one has water on the exoplanet. This is done during an exoplanet occultation, WASP 96b, and there's others, even better cases, like this 1100 light years. The near infrared spectrum shows features like water, but it has a temperature of 1000 Fahrenheit and half a Jupiter mass, so it's not an ocean planet like the Earth. This really is not water. It is steam, but there's H2O, all right. I won't speculate on life there, but at least it has the right building blocks. Yeah, there's already a claim of real aftermath of organic life, but there's also papers that have disputed that, so let's not go to that. So let's get to the cosmic circle of life. At the end of their lifetime, a star like the sun, not necessarily this central star, but the star in the middle of this nebula, will expel its outer layers when the hydrogen in the core and the outer shell and the helium in the core, the outer shell have done their nuclear burning, all converted to heavier metals. And then the star will start expelling its outer layers. It doesn't come in one phase, it comes in many phases. You can see the background galaxy here that these astronomers got very excited about. So it has exhausted the hydrogen and helium as nuclear fuel, and it swells up to about 100 times the current size. So it would engulf the Earth, maybe also Mars. This would be the end of our solar system. Yeah, so I couldn't resist showing that with the poet in scripture. For dust thou art, and unto dust shalt thou return. This is not only true for people, it is also true for planets and for stars. This is how the sun will end in 5 billion years. No need to sell your real estate yet, but that will happen. It's not a disaster, it turns out, because Andromeda will collide with us before that time. And the supermassive black holes may merge, so that may be more dramatic than this event. But I'm just saying, it doesn't look so good 5 billion years. This is the same image now in the mid-infrared, And the dust that is being expelled, the outer layers of the heavier chemical elements at 1% in the bottom of the periodic system, really starts forming dust. You know, silicon carbonaceous with lots of oxygen, magnesium, iron, what have you not, everything that's in the periodic system in the appropriate proportions gets expelled in these outer layers. And that will be the food from which new planets and solar systems can form. Here's the famous Northern Ring Nebula that you might have seen through a small telescope. This is it in full glory with the NIRCam and the MIRI. And so when a star like the sun loses its outer layers in what we call the asymptotic giant branch stage, this is what our solar system will look like in 5 billion years. And of course, it will at that point leave a hot white dwarf behind, typically half about the mass of the original star, have a solar mass that will illuminate this nebula to the beautiful shape it has. This process can also be more violent. You get 30 solar masses, you get a Wolf-Rayet star. Before it goes supernova, it will throw out its outer layers. If don't want to overinterpret this, but this nebula doesn't look entirely symmetric to me. It looks like it may be rotating in sort of an hourglass shape, possibly a fast rotating star that is also throwing out its outer layers before it actually goes boom and the center collapses in the supernova process. So this is the prelude to that stage. Again, for massive stars, dust thou art, and to dust shalt thou return. More dramatically so, of course, in supernova 87A, when I just started out as faculty member at ASU, I was in Las Campanas just after this happened. A beautiful sight to see that supernova. Since then, of course, the neutron star is there. The earlier shells imprinted by the late stage of the stellar evolution seen here is this hourglass feature that is still visible today, and of course it keeps expanding. Last example of this is the Cassiopeia A supernova remnant seen here in full MIRI glory with all the molecular features shown in different colors. The original star gone, but the outer layers expelled. Keep this image in mind because in the next two images, I'm going to make the case that this happens everywhere. This is the nearby galaxy M83. In the near infrared, the red indicates all the hydrogen locations. The blue indicate locations of the young stars that have just formed out of the hydrogen. In case of the bulge in the nucleus, it's older stars. And in the mid-infrared, you almost exclusively see the dust. So it's the other 50% of the star power shining at the dust wavelengths. And this is the dust in a similar, not quite identical spiral structure, ejected by stars in these spiral arms that went supernovae or went into their AGB stage earlier on. So for galaxies, it is also true that stars are made out of this dust, and those stars will also return this dust. So that is the cosmic circle of life. And it is true everywhere. All the galaxies that Webb has looked at, all the telephone numbers in your local directory show more or less the same, not identical, but similar spiral structure with older stars in the center, younger stars interspersed between the hydrogen, and then lots of, in this case, orangey colored dust. So cosmic star formation and dust production are ubiquitous throughout the universe, and the cosmic circle of life rules throughout the universe with the correct periodic system that I just pointed out. So I'm now halfway through. I'll take a few questions, good technical ones, and then I'll get to the main meat of the eyes of Einstein. Any questions? Feel free. Yes, please.
So you were saying that stars form at the tip of these fingers? in
Yes,
the
they
nebula?
do.
Why is that?
Because the gas is cool for it to have taken this shape. Initially, it may have been hotter, but it's cool, and the stars are very much shielded by this dust. And the radiation pressure from the hot stars, that star cluster you saw in other images, is
Mhm.
also present here but not shown. Pushes that gas and dust backward and then leaves the remaining gas that assembles itself in that new low mass star that becomes something like the sun with its own planetary system.
Hmm.
Yeah. This is not the only way it can happen, but this is a common way. And it produces the gas and the dust we see. Any other questions? Good question. Yes, please.
Oh, I was interested in that Venus planet that you talked about. When planets had a high temperature and water temperature.
Yes, I'll get back to that. Sorry, this wasn't.
Someone.
Yeah, okay. I want the right one. Yes, go ahead. That was before I got to this one, right? Yeah. What about?
So it's really interesting that it is steamy because a planet like Mars can maintain its atmosphere really off of space. And I was wondering if this was a very massive, I guess, planet that's sort of not involved with water.
It's half a Jupiter in mass, so it's quite good in holding on with its own gravity to almost all of the chemical elements. The Earth atmosphere has lost all its hydrogen, right? Because the gravity is not enough. The helium is sort of hanging around. In this case, hydrogen is still in the atmosphere and H2O is the prevalent one. Remember the periodic system, everything gets built in the same proportion. So water is actually a natural feature to have. Other planets will show that also, as well as methane and ammonia.
I just thought it was half Jupiter. Thank you.
Say again?
I missed that it was half Jupiter. Sorry.
Yeah, it's half Jupiter. Yeah. I didn't know that either. This is not my area of expertise. I thought these images were just too good not to show. Okay, so any other questions? First part. If you have any technical questions anytime, it's fine. I know a lot about the telescope. This cosmic circle of life is not my area of expertise. So here it is, the eyes of Einstein. We're going to view the universe through observing the many things that Einstein correctly predicted. Yes, doubted. Einstein predicted gravitational lensing. Didn't like to do it at all. In fact, one of his colleagues, one-page paper, colleague had asked him to write this paper. He starts the paper by saying, didn't really want to write this paper, but I'll do it to please my colleague anyway. And then he predicted the Einstein angle just exactly correct. And then he concluded the paper by saying, well, this is nice, but the angle is so small that you can never observe it. We'll get back to that. Then he predicted black holes. Actually, somebody else did with his theory. He did like that. He thought they were abominable. Well, they have abominable character, but they're also essential, as we will see. Predicted the Hubble expansion before Hubble discovered the Hubble expansion. Didn't like that either. So he introduced lambda. Then he called lambda his greatest mistake, which we have since then learned is not a mistake. It was an Dorfer Nobel Prize. Now, recently we have learned that maybe dark energy changes with time. So Einstein predicted all these things, and many of those he had honest doubts about. All right, so we start with Stephan's quintet, 4 colliding galaxies, 1, 2, 3, 4. This one in the foreground, they're not actually colliding, but these other 4 are colliding 290 light years away. These are cosmic train wrecks, which are much more common in the past. Galaxies merge, they form new stars. When they merge, you can see the Miri afterglow for star formation, like you saw in previous charts. With the spiral arms here, it's more irregular because the galaxy gets ripped apart during the merger. This is a minor merger, also known as a cosmic fender bender. Yeah, we also see more dramatic ones later on. This is the same in the mid-infrared, which shows the molecular gas much better. You see molecular gas hanging around, forming new stars. That's the foreground galaxy. This one in the north has a very bright point-like source in the center. That is the, in the top galaxy, gravitational collapse in the center. One epoch in the past caused the supermassive black hole to grow, and currently the black hole is feeding via an accretion disk on material. Of course, the black hole itself can't emit light because the speed of light would be smaller than the escape velocity, and theoretically at the Schwarzschild radius, so nothing can escape the black hole. But the accretion disk gets ultra bright and can be seen especially well at mid-infrared wavelengths through the dust. This is an ordinary galaxy, 1433, 48 million light years away. Again, we see the beautiful spiral arms. Sorry about that, where that came from. And the pockets here in red are the H2 regions. Here's another one, 4796, that clearly has the asterisk-like feature, the point spread fracture telescope in the center, another central supermassive black hole. That is actually quite common. The more you stare at these images, here's a very blatant case. Don't feed this animal. It's a secret galaxy about 220 million light years away, got an ultra bright core. You can see there's clearly a galaxy there with spiral arms and a central bulge, but the supermassive black hole is feasting on the infalling gas. And also gas is not only falling into the black hole producing this accretion disk, but also being expelled in perpendicular directions, as the spectrogram of this object has shown. One of our own images, one of the first we actually got in July of 2022, was this overlapping galaxy VV191, a relatively nearby galaxy, a redshift 0.05, so it's about 750 million light years, I think. So a spiral like our own, not our own, but like our own, the sun looking here is where our galaxy, about 2/3 of the way from the center to the edge. And this spiral galaxy is right in front of this elliptical on the left. The elliptical, other than its companions and background galaxy, is pretty irregular in shape. So if you model the light profile of that galaxy, assume it's a Sersic profile or something, I'll spare you the details, you can actually predict how much light from the elliptical is behind each one of these spiral arms. And you can directly measure the extinction or dust attenuation of these spiral arms. This is in a paper by my co-author Bill Keel a few years ago. And more recently, my student Jessica Berkheimer has identified 150 kilometer clusters in this elliptical, cutting out the region covered by the spiral. This is shown better here. We get a little technical now. We plot the 0.9 micron magnitude versus the 0.9 minus 1.5 color. This horizontal line, this slanted line, is the completeness limit. And most of these dots are globular clusters, about 150 of them, in that background elliptical galaxy. And there is an array of data points here between 10�7, 6.5, 10�6 solar masses with various ages. The ages are generally 13 billion years, and metallicities that range between around solar and 1% of solar from red to blue. So that's low metallicity. This is high metallicity. And you can see most of the globular clusters. You can see it is rather large distance, rather than 27 magnitude or absolute magnitudes of around -10. And that is a nice sample. That sample will get a lot better for other data sets, as you will see in a minute. We do this now regularly, measure globular clusters in galaxies other than those Hubble has done in our own solar neighborhood. You can do from the ground very close by, like in the Virgo cluster or local group. Here's that same elliptical again. On close inspection, you see an arc-like feature here at 10 o'clock with a counter image here at 4 o'clock. This is actually a gravitational lens. It's not caused by a cluster. It's caused by the lensing property of this massive elliptical, which is several times 10 to the 10 solar masses. It's not a huge galaxy. And it lenses a background galaxy, a redshift of 1, into an arclet, basically because there's various light paths from this galaxy. The original galaxy would look something like this. That happens to be right here behind the elliptical. And then the various curved light paths lead you to see this beautiful arc. And that was measured. We have an Einstein angle for that thing and an enclosed mass of several times 10 to the 10. This was probably our best image, full 30 hours of Webb of the cluster redshift 0.4 called max 0416. We'll get to it more in a minute. It was on the front page of the New York Times in the science section. And they labeled it, it's Christmas time, cosmos. How do I make this thing go away? Am I not sharing the screen?
You are,
Yeah.
you go,
Oh, okay, yeah, okay, good. Sorry about that. Missing the title here. We can move this thing. Oops, something happened. Need to go back now. There. Sorry about that. Sorry, going the wrong direction. I apologize. So that was our, let's go away to, there we go. Oh, good to have a mouse. All right. So along some of these arclets here, which of course are highly stretched in the galaxy, some go through the perimeter of the cluster, distant galaxies that get imaged multiple times because of the gravitational curvature of this space. In this particular object over here called Orville, a redshift 1, there were 12 new stars discovered from the 4 epochs we had for this cluster that went across the infinity curves. And in this particular arclet, there was, we'll show in a minute, a binary star, a redshift 2, and a sweet spot where the magnification was a factor of several thousand. And we can, courtesy of this gravitational curvature, we can see most cases that these images come with 2 images on each side of the critical curve, B and B prime, C and C prime. But this lens star, which turned out to be the double star, is almost right at the sweet spot and therefore undergoes a magnification factor of 1,000 to 4,000 in 2 papers by Jan et al. And Diego et al. And the spectrum we have for this object is not well fit by an individual star, but by a red and a blue star component of 5,000 and 14,000 degrees. There were also in this other pizza slice looking object called the wormhole, a good number of stars that flared up between the various epochs, not because they were variable stars, but because they went across in the source plane, not the image plane, what we call the caustic, the critical surface, where momentarily the magnification can get very high because the lensing cluster moves in the foreground front of these very distant stars. We can see them vary in time at extreme magnification. So we're now studying individual stars at redshift 1, not star populations, but individual stars. This is only possible because their magnification is factors of 1,000. These magnifications only last for a few months, depending on how fast the cluster is moving and the stars themselves are moving. But it's like, seeing 7 magnitudes fainter below the detection limit, only possible. This is the best color rendering we have of this cluster, 122 hours with Hubble that provides the blue light, as I argued in the first slides, plus 22 hours with Webb. You can see some very blue objects in the foreground by Hubble, and then these very red dusty things, including some of these objects that they call little red dots in the background. Also, globular cluster studies were done here in the various color magnitude diagrams down to these completeness limits. And this data is now good enough, redshift 0.4, to outline the range of masses and ages and metallicities between high metallicity and low metallicity for these objects. This is also a paper by one of my students, Bergheimer et al. So Webb is measuring these globular cluster masses and ages over cosmological distances. This is a big deal because this is really hard to do for Hubble, and Webb can do it routinely. One last glance at the difference between Webb and Hubble. Hubble, Webb, Hubble, Webb. And remember, the Hubble image is 6 times longer than the Webb image, but they reach about equal depth. So one telescope is 6 times bigger than the other. So they reach roughly equal depth, different wavelengths. Okay. Here's what we call the Biden cluster. This was the one that President Biden himself revealed the day early. Data was supposed to come out July 12th. One of my team members picked this target, another one reduced the data, and Tom Cookamore and Dan Coe, they sent it up to the SDSCI director, who fell off his chair. She sent it up to Goddard. Well, the center director fell off their chair. And they sent it on to NASA headquarters, where the administrator fell off his chair, sent it on to the OMB, which sends it on straight to the White House. The president himself reveals it. Fortunately, during the press release on July 11, President Biden was called out of the meeting by his national security advisor, so he didn't have time to scoop us on the Nature paper. The important thing here is that these galaxies, seen a redshift of 0.4, are 9 billion years old at that time. This was when the Earth was born, the sun, 4.5 billion years ago. So these galaxies today are 3 times older than the Earth today. Yeah, keep that in mind. That's the Hubble image, Webb image. So big progress. All right. Now we get to the more exotic, more distant ones. Here's a redshift 10, 500 million years after the Big Bang by Coe et al. On a cluster with this telephone number, an object that is behind the cluster image here, there, 3 different locations, actually a double galaxy, yellow one and a redder one, a fraction of a kiloparsec apart, seen on the 3 different angles, of course, because there's 3 different light paths to this doublet. And this is what Webb has now been doing routinely. Here's another example of Arundel by Welch et al. A highly lensed arc, redshift 6.2. Again, there's a symmetric part, not very symmetric, but symmetric enough to get rid of the Earth. Also out here. And this Arundel is a star, also a binary star. Some people have argued part of a star cluster, the most distant star observed ever directly. The magnification is a factor of 9,000, a paper by Brian Welch. So light paths are straight in 4-dimensional curved space-time. And you can see that here. And if you're right at the sweet spot, which is right around this symmetry line, is where you can get this very high magnification temporarily. Here's probably our best image. This is G165, one of the Planck mission selected far infrared clusters, a redshift 0.35. Adia here and other folks have worked on this as well, trying to model the lensing. 2 very massive piles of galaxies coming in triplets or more, 2 separate centers of gravities that have lensed the background galaxy, not unlike this one, or one in the far corner, but highly stretched along 3 different light paths, and then another one, redshift 2.3. There's actually various redshifts involved here, but the main ribbon here is redshift 2.3, also imaged 3 times. And next to the bulge of this galaxy, and mind you, the galaxy unlensed would look just something like this. I have images somewhere. The little dots here and there, 3 different parodies that we discovered on March 30th, 2023. We recognized it could be a supernova. We got 2 more images within 2 months from the director and the spectrum. The supernova is a 1A, a redshift 1.78. And if you do this carefully, difficult job to do, the Hubble constant is 75 at that redshift today, with a rather large error, so measured 10 billion years ago. Here's another rendering of that where you can see the supernova. So this is all imaged volts, the galaxy and the supernova, same location. Adia here has much better model than I can show here, seen only 3.6 billion years after the Big Bang. So we have 3 epochs, a 9-point light curve, because there's 3 different relativistic light paths of that supernova to the detector. So we can estimate the Hubble constant directly. 4 papers in print with several others to follow. And the point I'll make is that the star formation rate of each of these highly star forming kind of selected galaxies is 2 to 350 solar masses a year. So if all is well, we should expect at least another lensed supernova a year. So if you observe it often enough, you're going to see more of it. There's the supernova light curve, 2 different filters, 9 data points, of course, 3 times observed, 2 others for free. You see it clearly looks like a supernova type 1A. There's our best measurement. Here's Adam Rees's value, and there's the microwave background value. So it helps to enhance the tension between the high values and the low values a bit. We would need more of these measurements, more supernovae, to make better case. This is completely independent of any of the other steps that folks take nearby. As I said, we predict more than once lens supernova a year, and there is other clusters that can do this even better still. Here's another one called J108 by my student Nick Fuerdal in press, and another paper by Kamineski. Very highly lensed background sources, extreme beautiful mess. Sorry, I can take a sore throat on it. With ALMA images, some of which, this one in blue, resemble the rotating disk with rotation curve. Others, like the one embedded in red, look like a merger with a sort of distorted rotation curve. This highly stretched banana here in green is more of an irregular object with no clear rotation. And this one over here in purple is a highly chaotic object. ALMA, of course, is very good in giving you the molecular structure of the velocity, while JWST is very good in giving you the continuum images, and the combination thereof is very powerful to figure out exactly what the star formation rate is for all these objects. The answer is very high, many hundreds of solar masses a year. We surely hope, according to the calculations anyway, these clusters should provide a good number of lensed supernova over the next number of years. Here's the paper by Kamineski that makes that point. Basically, for a number of clusters, he calculated the medium time delay versus the Einstein angle. You know, more or less a nice straight line for these clusters. And then he calculated the supernova 1A rate with the time dilation in there for these 8 or 10 clusters that he picked, 5 of which are the best. That supernova rate should be here, high, you know, fraction of a supernova per year for each of the clusters. Observe few of these clusters, you should get a bingo. And here's the core collapse supernova rate, which is much higher, of the order of unity at these redshifts. So in other words, if you observe these beasts a few times a year with JWST, you are bound to find more than supernovae, although they won't all be type 1H. Yes, please.
But the SFR is for the source, not for the cluster. You would need a source to have some.
Correct. Yeah, but in JO8, star formation rate, as well as with the G165, not the cluster, that's correct. It is the star formation rate of these objects is quite high. It's several hundred solar masses.
This was the pacifist paper,
Yeah.
But so so one thing I'm wondering about is even if you want to monitor these for supernovae, they're dusty at the end of the day. They're very dusty. So
Yes.
how are you actually going to observe a supernova? How are you getting past all that extinction?
That's a good point. I have another chart on that. Kamineski discusses that in great detail in his paper. You need to get somewhat lucky that supernova is not in a very dusty region. When you properly de-lens the object, you can figure out what the ASIM-V was in that region.
One of the criticisms we get from the lens supernova headshot measurements is, and this is really dependent on whether they agree with Adams measurement or agree with the CMB measurement.
Yeah.
But is the sample biased in some way? And by selecting supernovas with the most massive clusters, are you?
That's a good, so the clusters themselves, all they do is lensing. The question is the source of the background biased? The point clusters, yes. The JO8, maybe you know better than I do how passengers was selected. I think there was the far infrared selection there, but they were not as extreme as the other point cluster I talked about. So yeah, you do get a high supernova rate by selection, otherwise you wouldn't see any. Couple of others, here's the supernova Hubble saw in this cluster here. Well, the name's not listed, but okay. And then Webb later saw another one in 2023, so 7 years later, redshift 1.9. So that is called supernova encore, the gift that keeps on giving. And our hope is that with Webb we can eventually do enough of these that we can see some more. Here's another one in this RSJ cluster, 2.9 billion light years away. Supernova was only seen in one of the 3 lens images let's see, what was it now over there? Was not seen in the other lens images, so you have to get lucky and sometimes you will just miss it. So the beauty of this method is that you have completely independent from the microwave background estimate to the distance. The complication is, as you say, there's dust, you need to get lucky and observe it 3 times. This one is the massive cluster Abell 2744, 10 to the 15 solar masses, 4 billion light years away. There's 5 young galaxies here, 1, 2, 3, 4, 5, imaged redshift 7.8, 13 billion years ago. So Webb here is looking back 650 million years after the Big Bang. Yeah.
With individual stars that were magnified because they were close to the caustic,
Yes.
the time scale for them to sort of get far enough away from the caustic to disappear was months.
Yeah, it's months. So if you do the calculation, the magnification is typically a factor of 10 to 20 over the square root of d, where d is the distance to the caustic in arc seconds.
Okay,
And so if you're, the star itself is 10 to the minus 10 arc seconds across.
so that is a similar time scale to the decay time of the light curve for the supernovae. So if they start off close to a caustic and then move away.
Then that would be a problem. But that supernova hope, as we called it, this guy over here, wasn't close to a caustic. It just happened to be at the right location to be seen 3 times. Yeah.
So that would have to be folded in somehow to the.
Yeah, if
recovery
it
problem.
were right on the caustic, you would have that problem. That is true. Here is El Gordo, the most massive cluster. Lensing some background object in very nice linear pencil. That is, like Laurel Hardy. This is the thin one. This is a very massive cluster, redshift 0.9. At the very edge was this horseshoe type thing. We call Recaminescu called it El Anzuelo, which is Spanish for the fish hook. In El Gordo, Bill Harris has measured the globular cluster population the same way you saw before. We have that now for a whole range of galaxy clusters between 0.2 and 7 billion years back in time. So we're actually begin to start measuring the stellar evolution for high and low metallicity as a function of cosmic time. You can see the stellar population of these uniform quote unquote globular clusters does evolve over time. They were somewhat brighter in the past by a good bit actually, but that's half a Hubble time ago. And this is in the paper by Bill Harris et al. I want to call attention to this cosmic horseshoe here. I don't have the unlensed or the delensed image that's in the Kamineski paper, but it's a spiral galaxy with more dust on one side of the pulse than on the other side. You should read this story by Werner Salinger. Einstein never saw these images, right? He thought they could never be observed. Werner Salinger was a Holocaust surviving Jewish boy before World War II, who was the audience of a talk I gave a few years ago on this. He said, Roger, I knew Albert Einstein personally. I moved with my parents to Princeton in 1933, and Einstein would take me into his study and play the violin. So story over there is about Werner Salinger and how he met Albert Einstein. Albert never saw these images, but Werner Salinger did. So probably one of the most extreme cases is this highly stretched spiral galaxy called the Dragon's Arc in Abell 370. 44 individual stars around this critical curve that are flaring up and down, not because they're variable, but just because they go across the critical curve. So we're now detecting stars at redshifts bigger than 0.7, routine paper by Fudamoto et al. And hopefully someday we will get a lensing corrected initial mass function. Something that I think is even more exciting. If you look at the distribution of these flaring up stars compared to the best guess of the critical curve, in a cold dark matter model shown here, that distribution should be symmetric, as this what's the cold dark matter, this green curve indicates. The data, this histogram, shows that more of these caustic transits happen on one side than the other side, which is more consistent with a wave dark matter or psi dark matter model, in particular the ones where the energy of the conceived dark matter particle is a tiny 10⁻22 electron volt, and the Broyle radius or the Broyle wavelength of that particle is of the order of tens of parsecs. And that model seems to be this asymmetry that you expect in where the objects appear compared to the critical curve, caustic, is a property of one dark matter that seems to be consistent with this data. Yes, please.
How long is the, so it's because of the star's proper motion crossing over the caustic?
No, we wrote actually a paper on this in 2018, Windhorst et al., predicting how this would happen at redshift 7 and beyond. It's actually the motion of the cluster colliding parts like an El Gordo of the order of 1,000, like a bullet cluster being extreme, 1,000 kilometers a second. That's much bigger than the proper motion of these stars at redshift 1 or 7. Yep, so it's the cluster motion, the lateral motion that does it.
I'm just thinking like, it's a very science fiction kind of question, but could you get a exoplanet transit like curve around one of these lines?
That has been proposed. And people have even proposed to do lens Cepheids and stuff like that. I think that's pushing it a bit, although I have my name on the paper that proposed it. Lima Diego is the expert. Yeah, I won't go any further than that, please.
On a previous slide, I'm wondering, what do you think are some contaminants to this curve? Like, are they accounting for foot structure? Like, is there anything that could lead us to getting this curve wrong?
Very good question. So if you have primordial black holes or small mini halos along this line of sight, that could distort the model. Again, Kema Diego has written papers on this and even set constraints to intergalactic black hole masses and stuff like that. Yeah. It gets complicated. It's not a nice, clean measurement, but it's interesting enough to pay attention to. Then last but not least, I want to point out to this paper, especially dedicated to our colleague George Smoot, who passed away a few months ago, by Pozo and Broadhurst et al. In Press for Nature Astronomy. JWST and HST galaxies are more often elongated, prolate, cigar-like than round. You can see that here, Philomena, we just didn't cherry pick them, we just show a couple of things that are, predominantly cigar shaped. And then warm dark matter predicts, with the appropriate, the Broyle wavelength thrown in there for these light particles. More of that elongated features than cold dark matter, which gives you more rounder clumps. To quantify that, this of course is qualitative. You can plot the three-dimensional, ellipsoid, major axis, minor axis, and B axis, those ratios. This would be the place where you get the oblate or footballs. This would be the place where you get prolate cigars. This would be the place where you get the three-dimensional spheroids. For cold dark matter, that distribution would be different. And the data is in these elongated contours. You see, the data is more consistent with these numerical predictions for the psi dark matter or the wave dark matter compared to the cold dark matter model, where the distribution predicted is off from what is being observed. So cold dark matter makes galaxies that are too round and too large, while warm dark matter, psi dark matter, doesn't seem to have that problem. Doesn't prove, therefore, that this is a valid improvement of cold dark matter. I'm running out of time. Yes.
Quick question on your left.
Yeah.
Are you drawing the connection here between the shape of the galaxy and the dark matter distribution? It seems negative. Right?
Yeah, what these guys did is detailed hydrodynamical simulations with either pure cold dark matter, in which case you get more rounder objects, or with the filamentary structure that's inherent to the warm dark matter or psi dark matter models. And so one simulation has more filamentary structure than the others. And the question is, what does real nature show? The way to quantify that is in this graph. Show, well, the warm dark matter, psi dark matter predictions, these data points, well, prediction points, are more consistent with the data, which are these contours. You can see that here too, compared to cold dark matter. I won't call it the proof, but it's a good smoking gun.
But to be clear, these are not the these are not sort of the components of the dark matter halo, these are the components of the galaxy. So.
Yeah,
Okay, so
Yeah.
just making.
Yeah.
sure, but-
yeah, these are small scale simulations. I should move on. This is cluster redshift 1. There's a set of protoglobular clusters here, redshift 10, highly lensed. I want to conclude with that. With various SEDs, there they are, rather symmetric pile of globular cluster images, both sides of the curve, except this object E1. Important point here is they're all 50, 40 million years old at redshift 10. So they were born at redshift 11. Why is this important? The object got born at redshift 11. You observe them as globular clusters today. You should observe them as 30 billion years old. Scratch, that's what we see at all the lower redshifts with the globular cluster stuff we've done so far. That a consistent picture, maybe not quite yet, but we're certainly homing in to what Alan Sandage wanted to do for a long time, that Bill Harris is doing now. I'll skip that for the sake of the argument. I'll skip the relativistic jet. I'll conclude by stating that in the redshift cosmic time picture versus the black hole mass, black holes, and observe, of course, the redshift 6 and lower, we see log 10 to the 8, 10 to the 9 solar mass black holes. And these things would have grown over cosmic time along any one of these scenarios, addington or super addington. And that results in, compared to the local population here in red, black hole mass is not just 1% or less of the bulge mass, but it can be as high as 10% or even close to not quite 100%, but significant fraction of the bulge mass of the galaxies. So this results in overweight black holes compared to the host galaxy papers by Maiorino and from the earlier NERSPEC work. So the good old question, what came first, the chicken or the egg, the galaxy or the supermassive black hole? Mostly the egg came before the chicken. I had another chart of that, but for the sake of time, I won't show that. Last plot then, the growth of stellar mass over cosmic time between Hubble and Webb's well summarized here. Solar masses per year peaks at redshift 2, as I said, and then declines. The same for the AGN activity with wider error bars, a fairly consistent picture. Here's the ratio of the two. Stellar mass growth, black hole growth, the ratio mostly flat over cosmic time, but in the last 10 billion years or so, the black holes actually slightly outdo the stellar mass growth because the stellar mass growth declines so quickly. And of course, we have learned from JWST that it's a very large number of red dusty AGN that JW now sees at redshift bigger than 4. That supermassive black holes started growing fast before the first galaxies, or right around that time. So I'll put my conclusions up and run off the page. Sorry I didn't catch that before I recompiled it. I've said all that, so I won't repeat it. So I'll give you the conclusion. Webb has, in the form of the shape, in the form of cosmic dust, we were made from that as solar systems and as galaxies. That same dust is being returned in this process. And Webb is now measuring stellar populations, globular clusters in particular, and large stars, that's stars over cosmological distances, to the point that we can start to understand the initial mass function and the stellar evolution over a wide range of cosmic time. Thank you very much. Sorry, my voice.
Well, so we've had lots of questions for Roger, and we're getting to quite near time, but I think we can squeeze in 1 or 2 more. Is there any quick personal questions?
Maybe I'll ask one. So.
Yeah.
So you said the Webb galaxies are a lot more of them look like the cigars and elongated.
Yeah.
So that refers to those earlier galaxies at high redshift. Otherwise, we would have seen them before.
Yeah. It's not so much true today anymore because galaxies.
But then besides the interpretation of this warmed up simulations, what is the structural properties of galaxies at early times different?
What we've seen with comparing ALMA to JWST, the motions seem to be more chaotic. Start with mergers and it takes a while for to develop a couple of revolutions. Yeah, so galaxies are more chaotic, hierarchy. Not all, but sometimes you see small disks that are already rotating, that probably were more chaotic even higher.
Right, but I'm saying that, what Webber has discovered are high redshift galaxies, most of which are kind of just forming the disk. So we should be more elongated disk like, compared to
Yeah.
low redshift stuff.
And what we see in the ABC diagram, the three axes of the ellipse, is that they're actually more the ellipsoid in the prolate regime than in the oblate or spheroid regime.
Okay.
That was unexpected. I didn't see that coming. Yeah. Great question. Other questions? Yes, please.
What about the galaxies that are based on?
The galaxies that are what?
Galaxies based on. So you are mainly like counting galaxies.
Yeah. Yeah, face-on galaxies are clearly oblate, right? They're like pancakes, so they do exist.
And yeah, and I see from my eyeball, it seems that some kind of, some of the galaxies may, that bit of interaction. They may like there are some.
Go back to, where did it go? Oh. Sorry, I got lost in my own chart here. Yeah,
For example, the second one, the third one.
Yeah.
Kind of like different components with different colors.
yeah. And that's what the hydrodynamical simulations show, right? That, well, the components are never smoother than never smaller than the Royal wavelength, but, this is maybe a good example. They come in pieces or clumps, but they exist along filamentary structures. I agree that that's more true for the data than for the model. And so the model probably needs to have a little more star formation physics in it to show how precisely these things will break out into star forming clumps. The star forming physics isn't always correctly encoded into that SPH code. Yes.
I was thinking of a quick question. Bounce off this whole shit.
Yeah.
So there's a much higher merger rate of high redshift.
Yes, by factor of several. Yeah.
By a factor of several, and wouldn't this, rather than warm dark matter, explain a little bit of the asymmetry of the nucleus? Or the fact that many, like you said, that these seem to be actually mergers or something, rather than a single galaxy that might have this.
We thought for a long time too that these are mergers, but if you look at the statistics carefully, in many cases, they're too long to just be a merger. A merger will just, maybe two more or less equal subparts will fly by and then feel each other gravity and stretch and tidal force and become one object. This looks different from that. I think we need to find a way to quantify that better. Yeah, this is only the first paper Nature astronomy. Take it for what it's worth. Nature tends to publish things that go away. And hopefully it will inspire people to do it more detailed than that. Yeah.
Well,
Yeah.
maybe we should also thank Roger again for this. I'm guessing there are more people that want to talk with him for longer. We'll be taking Roger to dinner. We'll be meeting out in front around 5:15.
Yeah.
I want to.
Okay, yeah,
Were there any Zoom questions?
I didn't see any.
Oh, thanks. Well, great question, Phil. Thank you for your attention. Okay. All right, now what we do. Sorry.
I'm gonna head home.
Yeah.
And I will see you at 11 and 5.
Okay, sounds good. And I will either be 213 or in Javier Vieira's room. He gave me his key. Remind me tomorrow night, I give both sets of keys. So I have 2 key rings. Back to you.
Okay.
Yeah, all right, thanks.
That would be nice. If you mind, more for this as well.
Yeah, I just send you something to have.
It's like that.
Yeah, that's actually the sweet spot where we playing.
It's how I collected it. I mean, I'll show you. You should.
Okay. Was this about the right level there, Gotham? Yeah?